Okay, let's unpack this. Carbon. Think about it.
Yeah.
You've got the humble graphite in your pencil, and bam, you have this incredibly tough, glittering diamond.
Yeah.
And here's a real mind bender. You, me, everything alive, we're mostly built from carbon compounds. What an actor.
It really is. What's fascinating is that very contrast, these incredibly different physical forms, all stemming from the same fundamental element.
Exactly.
That's precisely what we're exploring today, carbon chemistry.
Right, carbon chemistry. At its heart, it's the study of carbon and its seemingly endless ability to link up with itself and other elements.
Yeah.
I mean, forming practically everything around us.
Everything.
And for this deep dive, we've got a stack of information, various sources, articles, research that really highlights just how vital carbon is to our world, from like the tiniest atomic level to the vast systems of our planet.
And our mission really is to pull out the most important insights from all this material.
Yeah, deliver those satisfying aha moments, and keep it all clear and hopefully jargon-free for you.
Okay, so where do we start? Well, one thing that immediately strikes you from our sources is carbon's sheer ubiquity.
Right.
We encounter it constantly. Consider this. The graphite in your pencil, pure carbon. Diamonds, the ultimate in hardness, also pure carbon, even something as basic as charcoal. And it's worth noting, some hard coals can be, up to 98% carbon?
98%. It's literally everywhere. And it's not just the non-living stuff. Think about forests.
Oh, yeah.
The research highlights that they're made almost entirely of carbon-containing compounds.
Yeah.
So that giant oak, mostly carbon, that little dandelion pushing through the sidewalk, mostly carbon.
The scale is just astounding.
It really is.
And its role extends far beyond just being, a structural component of life. Our sources emphasize how carbon and its compounds are fundamental raw materials for a massive array of industrial products.
Like what?
We're talking plastics, detergents, the very food on our plates, and a huge spectrum of medicines.
And then there's the energy piece. Here's where it gets really interesting and maybe a bit more complex.
Definitely.
Oil, coal, natural gas. The fuels that have powered our world for so long are primarily made of carbon.
Right, the hydrocarbons.
And as we all know, our reliance on these fuels has led to some significant economic challenges, but even more critically, it's deeply intertwined with global warming.
Yeah, if we connect this to the bigger picture, the overwhelming scientific consensus, as indicated by our sources, is that burning these carbon-based fuels has significantly increased the concentration of carbon dioxide, CO2, in our atmosphere. And this increase is directly linked to the rising global temperatures we're observing.
We see the evidence, right? The melting Arctic and Antarctic ice, the retreating glaciers. These aren't abstract ideas.
Not at all. They're tangible evidence of this warming trend.
So the very element that builds life and powers our industries is also at the center of one of our biggest global challenges.
Okay, so carbon is everywhere and does everything, but our understanding of it hasn't always been this way, right?
Not at all.
Our sources touch on a historical shift in how we viewed carbon chemistry. Yeah, this raises a really interesting point about the evolution of scientific understanding. Originally, there was a strict division.
Okay.
You had organic chemistry, the study of compounds derived from living things, and inorganic chemistry, the study of compounds from non-living sources like rocks and minerals.
And they thought organic stuff was special somehow.
Exactly. The widely held belief was that a special vital force was necessary to create organic compounds, some kind of life spark.
A vital force. That sounds almost like magic. Like there was some essential ingredient that only living organisms possess.
Pretty much. But that distinction turned out to be incorrect. Our sources highlight a pivotal moment in 1828. A German chemist, Friedrich Wöhler.
Right.
He synthesized urea in his lab. Now, before that, urea had only ever been obtained from living organisms. Wöhler's experiment basically showed that a substance made in a lab could be identical to one produced by a living thing.
So no vital force needed.
Nope. It effectively dismantled the whole vital force theory.
So a lab-created molecule was chemically identical to a naturally occurring one. That must have really shaken things up scientifically.
Oh, absolutely.
Showing that the same fundamental chemical rules applied regardless of origin. Now, humanity's relationship with carbon stretches back ages, even before we grasped its chemical intricacies.
Way, way back. Our sources take us back to the earliest harnessing of carbon fuels, fire.
Fire.
Our ancestors were likely using fire as far back as 800,000 years ago.
800,000 years. That's an incredible span of time. Makes fire one of the very first technologies humans ever employed.
Definitely. Just think about the impact of that. The ability to cook food expanded the range of safe things we could eat.
Huge.
Plus, fire provided warmth, light, and protection from predators. It's hard to overstate how revolutionary that early connection with burning carbon was.
Absolutely. And that connection continued to develop, didn't it?
It did. Our sources mention the early existence of small coal mines in Europe dating back to the 1200s. By the 1700s, there was a significant demand for charcoal, particularly in metal production.
And that demand put a real strain on resources, didn't it? I recall reading that by the mid-1700s, there was heavy reliance on wood and coal to power steam engines,
Right.
leading to widespread deforestation in places like England and Europe.
Precisely. That scarcity of wood actually spurred the adoption of coke.
Coke.
Yeah, a fuel produced by heating coal. Coke was more efficient for metal production because it burned hotter and cleaner than regular coal.
Okay. And speaking of steam engines, that's another massive carbon-fueled invention that fundamentally reshaped the world.
Oh, undoubtedly. Developed in the early 1700s, these engines harnessed the heat from burning carbon to boil water, creating steam.
That powered all sorts of machinery pumps, steamboats, trains.
It was the key driver behind the Industrial Revolution, a period where the use of carbon-based fuels, primarily coal, just exploded.
Right. It transformed societies and economies globally. And coal remains a significant energy source today, doesn't it? Especially in heavily populated countries like India and China.
Very much so. Widely used in power plants there. But our sources also highlight the significant downside, the substantial air pollution generated by these coal-fired plants.
And it travels, right? That pollution isn't just local.
Exactly. What's particularly concerning is the global reach. One study mentioned in our sources found pollutants from a coal-burning power plant in China all the way in the mountains of California.
Wow. Really underscores that the effects of burning carbon are not confined to local areas.
Not at all. Then we have oil. It's interesting to learn that while we often think of oil as relatively modern,
Yeah.
the ancient Chinese were drilling oil wells way back. And before the mid-1800s, most oil was gathered from natural surface seeps.
Seeps. And what did they use it for?
Things like lamps, medicines, even construction materials, and natural gas.
That has its own fascinating history. It began with street lighting in the 1820s.
Streetlights. Yeah, followed by its use for home lighting later in the 19th century before the electric light bulb took over.
Right.
Today, of course, it's a crucial fuel for heating, electricity generation, and various industrial processes.
Our sources also provide a handy timeline, which really contextualizes this long relationship with carbon.
It's quite a sweep.
We're talking prehistory with the discovery of fire, the Egyptians using charcoal way back in 3750 BC.
Incredible.
Even using it to absorb odors from wounds around 1500 BC.
And it continues, right. Using charcoal for water purification, the Romans documenting medical uses of carbon in 157 AD.
The growth of coal mining in the 1200s, all the way to the Industrial Revolution in the 1700s.
It really shows the gradual but steady increase in our reliance on this element.
And then it fast forwards to more modern milestones. Davy identifying carbon in coal and diamonds in 1812.
Mendeleev, including carbon in the periodic table in 1869.
The first coal-powered electricity plant in 1882.
The commercialization of activated charcoal in 1901, the rise of the petrochemical industry in the 1940s.
The shift towards natural gas in the 1950s.
And then, the emergence of global warming as a major issue in the 2000s, culminating with global coal production figures in 2002.
The long and evolving story.
It really is. And to truly understand carbon chemistry, we need to zoom in, way in to the most fundamental level, the atom.
Okay, the atom.
Okay.
Our sources provide a good overview here. So atoms are the incredibly tiny building blocks of everything, with a positively charged nucleus at the center containing protons and neutrons, surrounded by a cloud of negatively charged electrons.
Right. And the number of protons is what defines the element. Carbon, for example, always has 6 protons.
Always 6. That's the key.
That's the defining characteristic. And the arrangement of those electrons around the nucleus dictates how an atom will behave chemically.
How it bonds and reacts.
Exactly. Atoms strive for a stable configuration, and they often achieve this by gaining, losing, or sharing electrons. This can lead to the formation of charged particles called ions.
Our sources also give credit to Robert Boyle, the English chemist.
Ah!
He first proposed the modern definition of an element, something that cannot be broken down into simpler substances by chemical means.
Which was a big leap from the ancient Greek idea of only 4 elements: earth, air, fire, and water.
Definitely.
Absolutely. And building on that, we learn about isotopes.
Isotopes,
Yeah.
right. Atoms of the same element, but with different numbers of neutrons.
Exactly. So carbon-12, carbon-13, and carbon-14 are all isotopes of carbon. They all have 6 protons.
But different numbers of neutrons. Does that change how they act chemically?
Nope, not really. This difference in neutron number doesn't significantly affect their chemical behavior. They still act like carbon.
But that difference in neutron number is key for things like carbon dating, isn't it?
Precisely. Our sources explain this well. Carbon-12 and -13 are stable, so their proportions in once living material remain constant after death.
Okay.
But carbon-14 is a radioactive isotope. It decays at a predictable rate.
So you measure how much C14 is left.
Exactly. By measuring the remaining carbon-14 relative to the stable isotopes, scientists can determine the age of the sample.
It's fascinating how this subtle difference at the subatomic level allows us to peer back into the distant past.
It really is. Our sources also acknowledge the contributions of alchemy.
Alchemy, trying to make gold, right?
Yeah, and despite its ultimate goal being unsuccessful, alchemy actually advanced the field of chemistry through meticulous experimentation.
How so?
Well, testing ores, developing ceramics, paints, dyes, these were all advancements made by alchemists through their practical work.
So even though they didn't make gold,
They learned a lot about materials and processes. It highlighted the importance of empirical observation, of actually doing experiments.
it's a good reminder that even pursuits that don't reach their intended goal can yield valuable knowledge. Okay, moving up in complexity, atoms bond together.
Right, they bond together to form compounds. A molecule is the smallest unit of a compound that retains the compound's properties, like a water molecule, H2O.
Got it. And then we have the periodic table, that iconic chart.
The Chemist's Roadmap, created by Dmitry Mendeleev in 1869, originally organized by atomic mass, although the modern version uses atomic number,
And carbon's number 6.
still number 6. And the table is arranged into vertical groups which show elements with similar chemical properties.
Like carbon's group.
Carbon resides in group 14, along with elements like silicon, tin, and lead. Being in group 14 tells us it has 4 electrons in its outer shell.
And that's key for bonding.
Absolutely crucial for its bonding behavior. And the horizontal rows are periods, showing increasing atomic number. And our sources mention trends in the table too, right? Like size.
Yes, atomic size generally increases as you move down a group and decreases as you move from left to right across a period. This organization really helps us understand the relationships between different elements and predict their behavior.
Okay, so we've gone from our everyday encounters with carbon down to the atom and its place in the periodic table. But where did all this carbon originate in the first place? Our sources delve into carbon's cosmic origins.
Okay, here's where it gets really mind-blowing.
Lay it on me. The creation of carbon, like most elements heavier than hydrogen and helium, occurs inside stars.
Inside stars.
Yeah, through a process called nucleosynthesis. In the extreme heat and pressure of stellar cores, protons collide and fuse to form heavier nuclei. Carbon, specifically, is formed by the fusion of 3 helium nuclei.
Wow. So we're talking about these massive nuclear furnaces in space forging the very building blocks of our planet and ourselves.
Exactly. And when these carbon-rich stars reach the end of their lives, they often explode in supernovae,
Right.
scattering the elements, including carbon, throughout the universe.
So that's where the carbon on Earth came from.
It's believed that our solar system formed from the remnants of such exploded stars billions of years ago. Plus, early Earth was bombarded by carbon-containing meteorites, adding even more carbon to its composition.
So it came from space, basically.
Which explains why carbon is the 4th most abundant element in the universe, after hydrogen, helium, and oxygen. We are quite literally stardust.
We are stardust. That's an incredible perspective. Now, getting back down to Earth, our sources mention that carbon exists in different physical forms called allotropes.
Yes, allotropes. Charcoal was actually the first recognized allotrope of carbon.
Makes sense.
In fact, the name carbon itself comes from the Latin word carbo, meaning charcoal. It wasn't until 1812 that Sir Humphrey Davy famously proved that diamonds were also pure carbon.
How do you do that?
By burning one using concentrated sunlight. Around the same time, he also demonstrated that coal was another allotrope. And of course, graphite, the material in pencils,
Right. Pencil level.
is another common form. This stark contrast in properties, soft graphite, hard diamond from the same element, really underscores the power of atomic arrangement and bonding.
So same element, vastly different physical properties. That's the fascinating thing about allotropes. And our sources also mention a more recently discovered form, fullerenes.
Yeah, this is interesting. Even though humans have used carbon for millennia, we're still uncovering new aspects. Fullerenes, discovered in 1985, are another allotrope where carbon atoms arrange themselves in spherical or tube-like structures, like buckyballs or nanotubes.
Buckyballs.
Okay.
And they have unique properties.
Very unique properties that scientists are still actively investigating for all sorts of applications.
From stardust to soccer ball-shaped molecules, carbon just keeps surprising us. Now let's delve more into how carbon behaves on a day-to-day or maybe molecule-to-molecule basis. Our sources detail its physical and chemical properties.
Okay, starting with physical properties. Carbon is a solid nonmetal, but as we've seen with allotropes, its appearance can vary dramatically: black graphite versus colorless diamond.
Huge difference in hardness, too.
Massive. Graphite is very soft, maybe 1 or 2 on the Mohs scale, while diamond is the hardest known natural material, a 10.
Wow.
Despite these differences, both have very high melting and boiling points. And of course, atomic number 6, atomic weight of the most common isotope, carbon-12, is approximately 12.
And then there are the chemical properties, which really dictate how carbon interacts with other atoms. This all boils down to its electrons, right?
Absolutely. It's all about the electrons. Carbon has 6 electrons arranged in 2 shells. 2 in the inner shell and 4 in the outer, or valence, shell.
4 in the outer shell, that's the important part.
That outermost electron shell is crucial. Atoms are most stable when their outermost shell is full, which for carbon means having 8 electrons, the octet rule.
So how does it get 8?
Carbon has a few ways: losing 4 electrons, gaining 4 electrons, or, most commonly, sharing 4 electrons with other atoms.
Sharing electrons, that's bonding.
That's covalent bonding, yes. Sharing electrons forms chemical bonds.
And carbon is a bonding superstar, forming single bonds, double bonds, even triple bonds.
Right. Single is sharing 1 pair of electrons, double is 2 pairs, triple is 3 pairs. It does this with other carbon atoms and with atoms of other elements.
Which leads to huge molecules.
Exactly. This incredible ability to bond in so many ways, especially carbon-to-carbon bonds, allows it to form long chains, branched chains, rings, the basis for the vast diversity of organic compounds.
And it even allows for some rather unique applications of pure carbon, like that recent trend our sources mentioned, memorial diamonds.
Yes, that's quite something. Extracting carbon from cremated remains or even hair from a living person.
From hair.
Yeah. And using that carbon to create synthetic diamonds as keepsakes, it's a very modern and personal way to think about carbon's fundamental presence in living things.
And making diamonds synthetically isn't new, right?
No, the technology to create synthetic diamonds from graphite has been around since the 1950s. The quality has improved dramatically, sometimes making them hard to distinguish from natural stones. Apparently, significant quantities are produced annually.
It really underscores the transformative power of understanding and manipulating the basic elements. Now let's move into the vast world of carbon compounds. Our sources give us some common examples.
Okay, yeah. We're talking carbon dioxide, CO2, which we exhale. Table sugar, C12H22O12, chalk, calcium carbonate, KCO3. Natural gas, which is primarily methane, CH4.
And there's so many, they have naming systems, right, based on structure?
Yes, because there are millions of carbon compounds. They're often grouped and named based on the number of carbon atoms, the types of bonds involved, and any attached atoms or groups. For example, the prefix meth indicates 1 carbon atom, and the suffix -ene indicates only single bonds, hence methane.
Okay, and one major category is hydrocarbons, just carbon and hydrogen.
Correct. Hydrocarbons are molecules composed solely of carbon and hydrogen atoms. These include alkenes, 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 and aromatic hydrocarbons.
Let's start with alkenes, single bonds only.
Yes, alkanes like methane, ethane, propane, and butane contain only single bonds, and their names end in -hane. Many are obtained from separating crude oil.
And they're fuels, mostly.
Primarily fuels. The first 4 are gases at room temperature, like natural gas or propane for your grill. Then we have liquids like pentane and octane, major components of gasoline.
Right, octane rating.
Exactly. And then longer chains found in kerosene, jet fuel, and diesel. It's interesting, alkanes are also found in the atmospheres of gas giant planets and were likely a significant component of early Earth's atmosphere.
Okay, then alkenes, they have double bonds.
Alkenes contain 1 or more carbon-to-carbon double bonds, and their names end in -ene, like ethene, which is also called ethylene.
Ethylene. That sounds familiar.
It's a hugely important industrial compound used to manufacture polyethylene, plastic think milk jugs, plastic bags, also used in antifreeze, and even as a plant hormone that promotes fruit ripening.
Ripens fruit. Huh.
Yep. Propylene, a 3-carbon alkene, is used to make polypropylene plastic. Both polyethylene and polypropylene are polymers' long chains of repeating units. Poly means many, meros means parts.
Got it. Polymers, and then alkanes, triple bonds.
Alkenes have one or more carbon-to-carbon triple bonds with names ending in -lun, like ethane, commonly known as acetylene.
Acetylene for welding.
Exactly. These are less common in nature, but are found in some pharmaceuticals and are famously used in oxyacetylene welding torches because they burn at incredibly high temperatures.
And the last hydrocarbon group, aromatic.
Aromatic hydrocarbons contain carbon atoms arranged in a ring structure, most commonly the benzene ring, a 6-carbon hexagon with 3 double bonds, sort of alternating.
Why aromatic?
The term arose because many of the first discovered compounds in this category had pleasant smells, aromas. Many complex compounds feature benzene rings with other atoms or groups attached, replacing the hydrogens.
Okay, so that's hydrocarbons,
Yeah.
but there are tons of other organic compounds too, right? With other elements involved.
Oh, absolutely. Beyond just hydrocarbons, there's a vast array categorized by their functional groups.
Functional groups.
Specific atoms or groups of atoms that replace a hydrogen on the hydrocarbon backbone and impart characteristic chemical properties to the molecules. They define the family the molecule belongs to.
Like alcohols.
Exactly. Alcohols are identified by the OOH group, the hydroxyl group. Ethanol, which is ethyl alcohol found in alcoholic beverages, is derived from the 2-carbon alkane, ethane.
Okay, what else?
Carboxyl groups, COOH, are found in carboxylic acids, organic acids. They're also in fatty acids, which make up fats and lipids, and amino acids, the building blocks of proteins. Even soaps involve these.
Amino acids. We'll get back to those.
Definitely. Then there are esters, often formed from the reaction of a carboxylic acid and an alcohol. These are known for their pleasant fragrances in flowers and fruits and are used in perfumes and flavorings.
Ah, fruity smells.
Often esters. And amines, which contain nitrogen, usually an NH2 group, they're related to ammonia and are also crucial components of amino acids.
So many different types. And they all react chemically.
Yes, and all these diverse compounds participate in chemical reactions, the process of transforming one substance into another by breaking and forming chemical bonds. Reactants turn into products.
And carbon's bonding versatility makes its compounds key players.
Absolutely central. Carbon's remarkable ability to form so many different types of bonds makes its compounds central to a vast number of reactions.
Our sources mentioned a few main types of reactions.
They highlighted 3 common types in organic chemistry. Substitution, where parts of 2 reacting molecules are essentially swapped.
Okay.
Elimination, where atoms are removed from adjacent carbon atoms, often forming a double bond and a small molecule like water. Think ethanol turning into ethylene.
Right.
And addition, where atoms are added to reactant molecules, often across a double or triple bond, breaking one of the multiple bonds.
Understanding these basic reaction types seems crucial for figuring out how carbon compounds interact.
It's fundamental. Now, building on that, let's turn our attention to what are arguably the most crucial carbon compounds for us.
Yeah.
The molecules of life.
Biomolecules.
Biomolecules. These are the organic polymers essential for all living organisms. Proteins, for example.
Proteins. Building blocks and workers.
Exactly. They're polymers of amino acids and fulfill vital structural roles, like in your skin and hair and nails, and functional roles, like enzymes that catalyze almost all the chemical reactions of life.
And there are, what, 20 different amino acids?
20 common types, yeah. Each has a central carbon, an amine group, NH2, a carboxyl group, COO, a hydrogen atom, and a unique side chain, the R group, which makes each one different.
And they link together.
They link together via peptide bonds, formed when the carboxyl group of one reacts with the amine group of another, releasing a water molecule. Long chains are called polypeptides.
And they fold up.
They fold into intricate, specific, 3-dimensional structures. The sequence of amino acids determines the structure, and the structure determines the function, allows for an almost infinite variety of proteins.
Amazing. Okay, what's next? Carbohydrates.
Carbohydrates. Sugars and starches. They generally contain many hydroxyl OH groups and one carbonyl CO group, include sugars, starch, cellulose, glycogen.
Why carbohydrate? Carbon and water.
The name comes from their empirical formulas, which often look like carbon plus water, like glucose is C6H12O6, which you could write as C6H2O6. But chemically, they're more complex.
Okay. And there are different sizes.
Yes. Monosaccharides are simple sugars like glucose and fructose. Disaccharides are 2 monosaccharides linked together, like sucrose, which is table sugar. glucose plus fructose.
And polysaccharides.
Polysaccharides are long polymers of monosaccharides like starch and cellulose in plants and glycogen in animals.
And their job is mainly energy.
Primarily, energy provision. Breaking down glucose releases energy and energy storage. Starch is how plants store energy. Glycogen is how animals store readily available glucose. Cellulose is structural in plants.
Now, what was that about handedness in molecules?
Chirality. It's a fascinating concept. If a carbon atom has 4 different groups attached to it, it's called a chiral center. It can exist in 2 forms that are mirror images of each other, but non-superimposable.
Like your left and right hands.
Exactly like your hands. While these mirror image molecules, called enantiomers, are chemically identical in a non-biological setting, often only one of these forms is biologically active.
Really?
Yes. For instance, proteins in almost all life on Earth are built exclusively from the left-handed form of amino acids. The right-handed forms generally aren't used.
Wow. Okay, moving on. Lipids. Fats and oils.
Lipids, yes. A diverse group of biomolecules defined by being largely insoluble in water, includes fats, oils, waxes, and steroids.
They're important for.
Essential components of cell membranes. They also serve as highly efficient energy storage molecules, packing more energy per gram than carbohydrates or proteins.
So when we eat too much.
Our bodies store the excess nutrients as fat. It's also important to distinguish between saturated fats, which have only single bonds in their fatty acid tails and tend to be solid.
Less healthy.
Often considered less healthy in excess as they can contribute to artery deposits. And unsaturated fats, which have 1 or more double bonds, are usually liquid oils and can be beneficial in moderate amounts.
Got it. And the last big group, nucleic acids.
Nucleic acids, DNA, and RNA. These are the information molecules that carry our hereditary information and direct the synthesis of proteins.
Polymers again?
Yes, they are polymers of nucleotides. Each nucleotide consists of 3 parts: a 5-carbon sugar, deoxyribosin DNA, ribosin RNA, a phosphate group, and a nitrogenous base.
The bases are A, C, G, T.
In DNA, yes, adenine, cytosine, guanine, and thymine. DNA typically exists as a double-stranded helix. RNA uses the same bases except uracil, U, replaces thymine, T, and it's usually single-stranded.
And the sequence is the code.
The genetic code resides in the sequence of these bases in DNA. The sequence is transcribed into messenger RNA, mRNA, which then guides the ribosome to assemble amino acids in the correct order to make a specific protein.
And base pairing is key.
Absolutely. DNA replication and the transcription to RNA rely on specific base pairing rules. A always pairs with T, or U, in RNA, and C always pairs with G. This ensures accurate copying of the genetic information.
So carbon is truly the foundational element of all life as we know it, forming these incredibly complex and functional biomolecules.
Absolutely fundamental. Now let's broaden our perspective and examine carbon's role on a planetary scale with the carbon cycle.
The carbon cycle, okay.
Yeah.
Carbon is everywhere on Earth, right?
It's the 4th most abundant element on Earth overall, and a key component of our atmosphere, oceans, land, and all living things. And it doesn't just sit there, it's constantly being recycled.
Moving between different places.
Exactly. Moving between these different reservoirs, the biosphere, living things, the atmosphere, the oceans, and the land, geosphere. That movement is the carbon cycle.
And these reservoirs hold different amounts.
Yes, each reservoir holds a certain amount of carbon for varying length of time and has its own unique ways carbon enters and leaves. The biosphere, encompassing all living organisms, contains a significant amount, around 1,900 gigatons.
A gigaton is 1 billion tons.
1 billion metric tons, yeah, huge amounts.
And how does it move? What are the processes?
Several key processes drive the cycle. Photosynthesis is a big one. Plants use sunlight energy to convert atmospheric carbon dioxide and water into carbohydrates food, essentially.
Taking CO2 out of the air.
Exactly. Removing CO2 from the atmosphere and releasing oxygen as a byproduct. Chlorophyll is the pigment that captures the sunlight.
Okay, what else? Respiration.
Respiration. That's basically the reverse. Living organisms, plants, and animals break down nutrients, primarily glucose, using oxygen to produce energy for their life processes.
Releasing CO2 back.
Releasing CO2 and water vapor as waste products. The energy currency produced is ATP, adenosine triphosphate.
Weathering was mentioned too.
Weathering, the breakdown of rocks, also plays a role, especially chemical weathering, which can slowly remove some atmospheric CO2 over very long timescales as it reacts with minerals.
And what happens when things die? Decomposition.
Decomposition, yes. The breakdown of dead organisms by bacteria and fungi. This returns carbon to the environment. If oxygen is present, it breaks down fairly completely into CO2 and water.
But if there's no oxygen?
Without oxygen, you get partial decomposition. The energy-rich organic remains can get buried and, over millions of years under heat and pressure, transform into fossil fuels.
Coal, oil, natural gas.
Exactly. Coal, mainly from ancient swamp plants, oil and gas from marine organisms, typically.
And then there's burning.
Burning or combustion. Whether it's natural wildfires or humans burning fossil fuels or forests, it releases carbon, mostly as CO2, rapidly back into the atmosphere.
And human activity is a big factor here.
Huge. While natural fires are part of the cycle, the increased burning due to human activities, especially fossil fuels and deforestation for agriculture, is a major disruption. It adds CO2 and reduces the number of plants that can absorb it.
So let's look at the reservoirs. The atmosphere.
The atmosphere holds around 750 gigatons of carbon, mostly as CO2. It enters primarily through respiration and burning, with a slower release from the oceans, especially where warm surface waters release dissolved CO2.
And the oceans, you said they hold a lot more.
Vastly more, around 39,000 gigatons. Mostly as inorganic carbon-dissolved CO2, but also bicarbonate and carbonate ions, formed when CO2 dissolves and reacts with water, which also affects ocean pH.
So the ocean is a big carbon storage place.
It's a huge temporary resting place, acting as a carbon sink. It absorbs atmospheric CO2, especially in cold polar waters where the gas is more soluble and the water sinks, taking carbon deep down. Residence time is hundreds of years.
Are scientists looking at using that?
Yes, there's research into potentially injecting captured CO2 into the deep oceans for long-term storage, though there are ecological questions about that. Carbon also exits the oceans back to the atmosphere in warmer surface waters near the equator.
Okay, and the land. Rocks and soil.
The land holds the largest amount of Earth's carbon, by far, something like 65 million gigatons tied up in rocks, mainly carbonates like limestone, plus over 1,500 gigatons in soils as organic matter.
That's long-term storage then.
Very long-term. Carbon in limestone can last thousands, even millions of years. Fossil fuels represent carbon stored for millions of years. This land-based carbon is also an economically valuable source for us.
How does it get into the land?
Well, some was incorporated during Earth's formation. Then, decomposition of living things adds organic matter to soils, and the formation of fossil fuels locks carbon away over those millions of years.
And how does it leave the land?
Through volcanic eruptions, which release CO2 from magma, also through the weathering of rocks, and significantly through human activity mining and burning fossil fuels much, much faster than they are formed.
That's the imbalance.
That's the major imbalance driving current atmospheric CO2 increases. Human emissions from burning fossil fuels have risen dramatically, especially since the 1950s, due to population growth and increased energy demands.
So, to summarize the reservoirs and how long carbon stays there, rocks are millions of years.
Right. Rocks are the biggest and longest-term reservoir, millions of years.
Oh.
Oceans are large, residence time, hundreds of years.
Living things.
Living things, the biosphere, cycle carbon relatively quickly, minutes for metabolic processes, up to lifetimes of organisms. It's about 1,900 jitter total.
Soils.
Surface soils hold carbon for maybe thousands of years, and the atmosphere, hundreds of years for a CO2 molecule to be removed, though the overall concentration is changing faster now.
In carbon in living things, that's us and plants and animals.
Yes, about 1,900 jitter. Our cells are made of carbon compounds. Life processes, eating, breathing, reproducing, all involve moving carbon atoms around. Carbon enters organisms via food or photosynthesis and exits as waste, like exhaled CO2, and eventually through decomposition products.
Can ocean life help absorb more CO2?
Potentially. Algae and phytoplankton photosynthesis in the oceans already accounts for about half the oxygen we breathe, taking up CO2. There's research into enhancing this, but it's complex. And as mentioned, artificial carbon sinks, like deep ocean or underground injection, are being explored for long-term storage of excess human-produced CO2.
So the basic flow is atmosphere CO2, plants via photosynthesis, animals eat plants, respiration decomposition returns CO2.
That's the fast biological cycle, yes. Atmosphere to biological molecules and back again. Some decomposition carbon goes to rivers and oceans. Some gets buried as fossil fuels, which historically removed it from the fast cycle.
Right, upsetting the balance.
And ocean organisms with shells or skeletons made of calcium carbonate die, sink, and form limestone, another long-term removal, until erosion brings it back. Interestingly, the slight long-term imbalance, where photosynthesis slightly outpaced respiration over geological time, is what led to the buildup of oxygen in our atmosphere.
Which is good for us.
Essential for us. Burning fossil fuels, in a way, tends to restore that ancient carbon-oxygen balance, but it does so by increasing CO2 and slightly reducing our oxygen supply.
Okay, quick detour. Our sources briefly mentioned silicon-based life, like in sci-fi.
Yeah, the classic sci-fi trope. Silicon is just below carbon in the periodic table group 14, so it also has 4 outer electrons and can form 4 bonds. Chemically similar in some ways.
But it couldn't work for life.
It seems highly unlikely. Silicon's ability to form stable double and triple bonds is much weaker than carbon's. Critically, it struggles to form long, stable chains or complex ring structures like carbon does.
How long can silicon chains get?
The largest naturally occurring silicon molecule observed only contains 6 silicon atoms linked together. Compare that to carbon, which can form stable chains containing tens of thousands of atoms, essential for complex molecules like DNA and proteins.
So, no complex silicon life.
The chemistry just doesn't seem to support the kind of molecular complexity and stability needed for life as we know it. Carbon's properties appear uniquely suited. Plus, a carbon atom is inherently less complex than a silicon atom.
Fascinating. Okay, back to Earth systems. Let's turn our attention to the atmosphere and its critical relationship with our climate, which you mentioned is profoundly influenced by carbon.
Yes, the chemistry of Earth's atmosphere is incredibly complex, and we're still learning about all the interactions. However, it's clear that the carbon content, mainly as CO2, has a direct and significant impact on our planet's temperature.
And the atmosphere wasn't always like it is now.
Not at all. Early Earth's atmosphere, formed by volcanic outgassing, was vastly different. Probably lots of CO2, water vapor, nitrogen, maybe hydrogen sulfide, ammonia, methane. Very hot, and crucially, no free oxygen.
So life changed the atmosphere.
Fundamentally, the evolution of photosynthesis was the game changer. Photosynthesizing organisms started capturing sunlight energy, using atmospheric CO2 to make carbohydrates, and releasing oxygen as a byproduct.
And that oxygen built up over billions of years.
Exactly. It gradually transformed the atmosphere into the oxygen-rich environment we have today, roughly 21% oxygen. It's a remarkable coevolution between life, atmospheric composition, and the planet's climate.
Unique to Earth.
As far as we know, yes. This balance allowing for liquid water and moderate temperatures is unique. Compare it to Mars and Venus, which have atmospheres choked with over 95% CO2 and no significant photosynthesis to regulate it.
Now, it's important to distinguish weather from climate, right?
Absolutely. Weather is the short-term atmospheric conditions: rain today, sunny tomorrow. Climate refers to the long-term average weather patterns over decades, centuries, millennia.
And climate depends heavily on atmospheric carbon.
Very heavily. Even seemingly small changes in CO2 concentration can have significant and long-lasting effects on global climate patterns. And we know Earth's climate and CO2 levels have fluctuated dramatically throughout its geological history.
We had ice ages.
Roughly 5 major ice ages are known in Earth's distant past. These were periods of significant global cooling, expansion of continental ice sheets, and interestingly corresponded with drops in atmospheric CO2, maybe around 25% lower than pre-industrial levels.
Do we know why CO2 dropped?
The precise causes are still debated. Maybe geological processes, maybe changes in ocean circulation, maybe even overactive plant life drawing down too much CO2. The correlation between low CO2 and cold is clear, but the exact drivers are complex.
And the ice ages ended.
Yes, the last major ice age ended around 12,000 years ago, marking the beginning of our current warmer interglacial period, the Holocene. Why ice ages begin and end is also not fully understood, involving cycles in Earth's orbit, ocean currents, and greenhouse gas levels. But rising CO2 is definitely associated with warming trends.
And CO2 isn't the only carbon gas affecting climate.
No, while CO2 is the primary long-lived greenhouse gas driving current change, others like carbon monoxide, CO, methane, CH4, a potent but shorter-lived greenhouse gas, and synthetic compounds like chlorofluorocarbons, CFCs, also play a role.
Our sources mention that climate can change quickly sometimes.
Yes, research, particularly from ice cores and other paleoclimate records, indicates that global and regional temperatures can shift surprisingly rapidly under certain conditions, sometimes by many degrees within just a decade or two, much faster than previously thought.
Too fast for societies to adapt.
Potentially, yes. Much too fast for ecosystems and human societies to adapt easily. There's even evidence suggesting that abrupt climate change, like prolonged droughts, may have played a role in the collapse of some past civilizations, like in Mesopotamia around 4,200 years ago. Modern abrupt change in sensitive regions could have global consequences.
And CFCs. They damage the ozone layer.
Yes, CFCs gained notoriety in the 1980s for that. They are synthetic alkanes containing chlorine and fluorine, used for decades as refrigerants and propellants.
How do they hurt ozone?
In the stratosphere, UV light breaks them down, releasing chlorine atoms. A single chlorine atom can act as a catalyst, destroying thousands of ozone O3 molecules. This led to the thinning of the ozone layer, particularly the ozone hole over Antarctica that forms each spring.
But we banned CFCs, right?
Yes, the Montreal Protocol led to a global agreement to phase out CFC production. It's a success story of international cooperation. However, CFCs are very long-lived, and other ozone-depleting substances exist, so the ozone layer is recovering slowly, and the hole still forms.
Okay, this brings us squarely to the challenge of global warming. There's a strong scientific consensus here.
Yes. The Intergovernmental Panel on Climate Change, IPCC, which synthesizes climate science from thousands of researchers worldwide, concluded with high confidence back in 2007 and has strengthened this conclusion since that the recent increases in global average temperatures are very likely due to human activities increasing greenhouse gas concentrations, primarily CO2.
And this is based on a huge amount of evidence.
A vast body of scientific research observations of temperature rise, melting ice, sea level rise, changes in weather patterns, understanding of atmospheric physics, climate models, paleoclimate data. The evidence is comprehensive.
But the climate has changed naturally before.
Absolutely. Earth's temperature has naturally varied over billions of years. Ice ages were much colder, and atmospheric CO2 levels have also fluctuated naturally throughout history. The geological record generally shows high CO2 correlating with warm periods, low CO2 with cold periods.
Ice cores show this.
Yes, analysis of air bubbles trapped in ancient ice cores from Greenland and Antarctica gives us a direct record of past atmospheric composition, including CO2 levels going back hundreds of thousands of years. And analysis of the ice itself tells us about past temperatures. They showed a strong correlation between CO2 and temperature.
But the current situation is different.
The key differences are the rate of current CO2 increase, which is unprecedented in the ice core record, and the clear attribution of this increase to human activities, primarily fossil fuel burning, which adds old carbon back into the active cycle. While the precise magnitude and speed of future changes and all the feedback mechanisms are still areas of active research, the link between human-caused CO2 increase and warming is robust.
So what are the main human sources?
The primary human source of this additional atmospheric carbon is the burning of fossil fuels, coal, oil, and natural gas for energy in industry, electricity generation, and transportation. The combustion process converts the hydrocarbons in these fuels into carbon-based gases, mostly CO2.
Deforestation, too.
Deforestation, particularly through burning forests to clear land for agriculture, is also a significant contributor. It releases the carbon stored in the trees and reduces the planet's capacity to absorb CO2.
The EPA tracks U.S. emissions.
Yes, the Environmental Protection Agency estimates that approximately 90% of U.S. greenhouse gas emissions originate from the combustion of fossil fuels. These emissions contribute to both the greenhouse effect, global warming, and local air pollution like smog.
And there are efforts to reduce this.
Yes, regulations like the Clean Air Act aim to limit pollutants. Technologies like catalytic converters in cars, reformulated gasoline, computerized engine controls, and hybrid electric vehicles are all attempts to reduce emissions from transportation, a major sector.
What about the effects of the warming that's already happening or projected?
The projected effects are widespread and complex. Some localized areas might see temporary benefits, like longer growing seasons further north, but the overwhelming majority of projected impacts are negative.
Such as?
Increased spread of insect-borne diseases as warmer temperatures allow insects to expand their range. Changes in rainfall patterns making traditional agricultural areas unsuitable. Continued melting of glaciers and ice sheets leading to significant sea level rise and coastal flooding. And an increase in the frequency and intensity of extreme weather events like heat waves, droughts, and heavy rainfall.
Was the Kyoto Protocol an attempt to address this?
Yes, the Kyoto Protocol, which entered into force in 2005, was a United Nations agreement where participating developed countries committed to reducing their collective greenhouse gas emissions, primarily CO2. It used mechanisms like emissions caps and emissions trading.
How did it work out?
The goal for the first commitment period, 2008-2012, was a collective reduction of about 5% below 1990 levels for developed nations. Achieving significant reductions proved challenging due to economic costs and the need for substantial changes in energy systems and lifestyles.
Did everyone sign on?
Crucially, the United States, a major emitter, did not ratify the protocol. China and other large developing economies didn't have binding reduction targets under Kyoto. This limited its overall global impact, and the future of such international agreements remains complex.
The sources mention specific examples like France and wine.
Yeah, examples to illustrate potential impacts. Warmer temperatures could eventually make traditional wine-growing regions in France less suitable for certain grape varieties. Reduced snowfall in places like Switzerland could heavily impact winter tourism and skiing industries. These show the potential economic and societal consequences.
Okay, let's tie this back to carbon and our energy needs directly. Fossil fuels, where do they come from again?
They are the transformed remains of ancient plants and animals, buried under layers of sediment over millions of years. Intense pressure and heat converted this organic matter into coal, oil, and natural gas.
And they're all hydrocarbons.
Essentially, yes. All are primarily composed of hydrocarbons. When burned, combusted with oxygen, the carbon-hydrogen bonds break, releasing energy primarily as heat and light, and forming CO2 and water as the main products.
Let's look at coal specifically.
Coal is basically an impure sedimentary rock composed of very long hydrocarbon chains, often mixed with other elements like sulfur, arsenic, mercury, and mineral matter.
Advantages.
Its main advantage has been its relative abundance and accessibility. Surface deposits were exploited first, and now deeper mining operations are common worldwide. China and the U.S. are the top producers globally.
And its main use.
In the U.S., it's primarily used for electricity generation in large power plants, also used in some industrial processes like steelmaking.
Disadvantages. You mentioned impurities.
Yes, it's often considered a dirty fuel because its combustion releases not only CO2 but also significant amounts of pollutants, including sulfur dioxide, causing acid rain, nitrogen oxides, smog, particulate matter, and toxic heavy metals like mercury.
Mercury's a problem, right?
Yes, mercury gets into the atmosphere, deposits onto land and water, and then bioaccumulates up the food chain. High levels in large predatory fish like bluefin tuna are a concern for human consumption. The EPA is implementing stricter regulations on mercury emissions from power plants.
What about clean coal?
Clean coal refers to various technologies being developed, often with government funding, aimed at reducing the emissions from burning coal, either by capturing pollutants before they leave the smokestack or by improving combustion efficiency. However, the effectiveness, cost, and environmental impact of these technologies are still subjects of debate among critics and proponents. Capturing CO2 is particularly challenging and energy-intensive.
And acid rain.
Acid rain is caused primarily by sulfur dioxide, SO2, and nitrogen oxides released from burning fossil fuels, especially coal. These gases react with water, oxygen, and other chemicals in the atmosphere to form sulfuric acid and nitric acid.
And that damages.
It falls to Earth as rain, snow, or fog, damaging forests, lakes, aquatic life, and even buildings and statues made of limestone or marble. Technologies to remove sulfur from coal emissions, like scrubbers, have significantly reduced acid rain in North America and Europe compared to past decades, but it's still an issue in other parts of the world.
Okay, what about oil?
Oil, or petroleum, is generally considered a more versatile fossil fuel than coal. After refining, 1 barrel of crude oil yields a wide array of usable products.
Like gasoline.
Gasoline is the biggest product in the U.S., but also diesel fuel, jet fuel, heating oil, lubricating oils, asphalt and petrochemical feedstocks used to make plastics, synthetic fibers, solvents, fertilizers, and countless other products.
Disadvantages of oil.
Extraction can be messy and environmentally damaging, whether drilling on land or offshore. It involves habitat destruction, potential for spills during drilling or transportation, like tanker accidents or pipeline leaks, and water contamination.
And burning it still releases CO2.
Oh yes. Burning oil and its products releases CO2 and other air pollutants like nitrogen oxides and particulate matter. It's generally considered cleaner burning than coal. Less sulfur, ash, and heavy metals. But emissions are still significant, and regulations aim to reduce them. Scientists are also working on methods for removing pollutants like sulfur from fuels before combustion.
Natural gas. Demand is increasing.
Yes. Natural gas, mostly methane, is seen as a cleaner alternative to coal and oil for electricity generation and heating, as it produces less CO2 per unit of energy and fewer conventional pollutants. U.S. demand has been increasing.
But there are issues. LNG terminals.
Yes, transporting natural gas often involves liquefying it, LNG, and shipping it in large tankers. Proposals for more LNG import-export terminals raise environmental concerns about coastal ecosystems and security concerns due to the large volume of flammable material being handled. Fracking to extract natural gas also has its own set of environmental controversies regarding water use and contamination.
This leads to the idea of a carbon footprint. What is that exactly?
Your carbon footprint is a measure of the total amount of greenhouse gases, primarily CO2, produced directly and indirectly to support your activities. It quantifies your impact on the environment in terms of climate change.
Direct and indirect.
Direct is like the CO2 from driving your car or heating your home. Indirect includes the CO2 emitted to produce the food you eat, the clothes you wear, the electricity you use, etc.
And offsetting.
Offsetting refers to actions taken to compensate for your emissions by funding projects that reduce or remove an equivalent amount of CO2 from the atmosphere elsewhere. Examples include planting trees, investing in renewable energy projects, or capturing methane from landfills.
The sources gave examples of CO2 produced by activities.
Yeah, things like running a computer for a day, manufacturing plastic bottles or bags, producing a cheeseburger, driving a car a certain distance, all have an associated carbon footprint, helping to visualize the impact of everyday choices.
Looking ahead, energy needs are growing.
World energy consumption is predicted to increase significantly by 2025 and beyond, driven largely by population growth and economic development, especially in emerging economies.
And fossil fuels will still dominate.
Projections suggest that fossil fuels will likely remain the largest source of global energy for some time, simply because the infrastructure is in place and they are still relatively abundant and economically competitive in many regions. But as we've discussed, they are finite and their use drives CO2 emissions.
What about alternatives? Nuclear.
Nuclear power generates electricity without producing carbon pollutants, which is a major advantage for climate change. However, it raises significant concerns about reactor safety, the secure, long-term disposal of dangerous radioactive waste, and nuclear proliferation.
Renewables. Solar, wind.
Renewable energy sources, solar, wind, geothermal, tides, waves, biomass are clean in operation, no CO2 emissions, and inexhaustible. They are growing rapidly, but still represent a smaller fraction of total global energy compared to fossil fuels.
Hydroelectric.
Hydroelectric power, dams, is actually the most widely used renewable energy source globally, providing a significant amount of electricity. However, large dam projects can have major environmental impacts on river ecosystems and displaced communities.
Wind power is growing fast.
Yes, wind power has seen huge growth in some countries. Challenges include intermittency, wind doesn't always blow, visual impact, noise, and potential threats to birds and bats.
Solar.
Solar power, using photovoltaic panels or concentrating solar thermal systems, is very effective in sunny regions, and costs have fallen dramatically. Intermittency and energy storage, for when the sun isn't shining, are key challenges.
So renewables need backup.
Generally, yes. Because sources like wind and solar are variable, they often require backup power sources, like natural gas plants or large batteries, or sophisticated grid management to ensure a reliable electricity supply. As long as fossil fuels remain relatively easily obtainable and affordable, the transition to a fully renewable energy system faces significant economic and technical hurdles, though progress is being made continuously.
Okay, one last major area. Carbon in the products we use every day.
Right, it's not just fuel. Many essential industrial products are carbon-based. We've touched on pharmaceuticals, soaps, detergents, plastics. The list goes on.
Polymers are a big category here, natural and synthetic.
Exactly. Polymers are large molecules made of repeating subunits. Many natural products are polymers. Think wool and silk, proteins, cotton and starch, carbohydrates, natural rubber, latex and alkane polymer, hemp and flax, cellulose.
And synthetic ones.
Synthetic polymers include materials like nylon and rayon, often modified natural polymers, and of course plastics, neoprene, synthetic rubber. Plastics, as we said, are synthetic polymers usually derived from petrochemicals, those fossil fuel hydrocarbons. They are typically long chains of carbon atoms linked with hydrogen, and often other elements like oxygen, nitrogen, or chlorine. Many are transparent, and importantly, many types are recyclable, though recycling rates vary.
Drugs, too. Complex carbon compounds.
Very often, yes. Pharmaceuticals are frequently complex organic molecules with specific shapes that allow them to interact with biological targets in the body. Many were originally discovered in plants, especially those found in biodiversity hotspots like rainforests.
So biodiversity is important for medicine.
Critically important. Indigenous communities often possess traditional knowledge about the medicinal properties of local plants. Pharmaceutical companies engage in bioprospecting, collecting plant and animal specimens to screen for potentially useful compounds. Taxol, a highly effective cancer treatment drug, was originally derived from the bark of the Pacific yew tree. This also highlights the concern that deforestation could lead to the loss of potentially life-saving drugs before they are even discovered.
What about soaps and detergents?
Are essential cleansing agents. They work because they have molecules with two parts: a long hydrocarbon tail that is hydrophobic, water-repelling, and dissolves grease and oil, and a charged or polar head that is hydrophilic, water-attracting, and allows the whole complex to be washed away by water.
What's the difference between them?
Modern detergents often have long carbon-hydrogen chains with a sulfate, SO3, or similar group as the polar head. Traditional soaps are salts of long-chain fatty acids derived from animal or vegetable fats, combined with a metal ion like sodium or potassium. Legend has it that soap was first discovered by the Romans near sacrificial altars where animal fat mixed with wood ash, alkali,
Polyesters.
like dacron.
Polyesters are another important class of carbon-based polymers. Examples include dacron, mylar, and PEEK, polyethylene terephthalate, which is used for plastic bottles. The repeating unit contains an ester functional group.
What are they used for?
Dacron is used in tires, fabrics, like permanent press clothing, and even artificial blood vessels for surgical repair. Mylar is used for recording tape, shiny balloons, and insulating materials. PEE is ubiquitous in beverage bottles and food containers.
Nitroglycerin, that's an explosive, right?
Yes, nitroglycerin, C3H5N309, is a high-energy explosive. It's an organic molecule with a 3-carbon backbone linked to nitrate groups, containing nitrogen and oxygen.
Discovered by Nobel. It was discovered by Ascanio Saburo, but Alfred Nobel developed a safer way to handle it by absorbing it into diatomaceous earth, creating dynamite. Tragically, Nobel's brother and several colleagues were killed in an earlier lab explosion involving nitroglycerin. Nobel's vast fortune, made largely from dynamite and other inventions, was used to establish the Nobel Prizes after his death.
But it's also used as medicine.
Yes, surprisingly. In small controlled doses, nitroglycerin is used medically to relax and widen blood vessels, which helps relieve chest pain, angina, caused by restricted blood flow to the heart.
Teflon, the non-stick stuff.
That's the one. Teflon is a brand name for PTFE, polytetrafluoroethylene. Its repeating unit is C2F4, 2 carbon atoms bonded to 4 fluorine atoms. Fluorine atoms are very electronegative and form strong bonds with carbon.
And that makes it.
It forms long fluoropolymer chains that are incredibly resistant to heat, chemically inert, and have a very low coefficient of friction, meaning they're extremely slippery. Hence its use in non-stick cookware coatings, but also in things like low-friction bearings, waterproof fabrics like Gore-Tex membranes, and even coating bullet shells sometimes.
Wow. Okay, one last thing mentioned was nanochemicals. Carbon-based.
Yes, nanotechnology deals with materials on an incredibly small scale, nano-sized substances, smaller than about 100 nanometers, or roughly 3 billionths of a foot. Carbon-based nanomaterials like fullerenes, buckyballs, and carbon nanotubes are widely studied and increasingly used in various applications, from cosmetics and sunscreens to electronics and car fluids.
Are there concerns?
Yes, because these materials are so small and have novel properties, there are concerns about their potential environmental and health impacts if they leach out of products, accumulate in the environment, or interact with living cells in unexpected ways.
What did the study show?
Early lab studies suggested that buckyballs, for instance, could kill bacteria, raising concerns about potential harm to beneficial microbes or even human cells due to their ability to penetrate biological membranes. However, a later study mentioned in our sources indicated that when buckyballs were mixed with soil, they seemed to have no significant effect on soil bacteria, possibly because they clumped together or interacted with charged particles in the soil, altering their behavior.
So more research needed.
Definitely. Research is ongoing to better understand the life cycle, environmental fate, and potential health effects of carbon-based and other manufactured nanomaterials as their use becomes more widespread.
Okay, maybe a quick recap of some key glossary terms to tie things together.
Good idea. Acid rain caused by pollutants like SO2 from burning fossil fuels. Allotropes, different physical forms of the same element, like diamond and graphite for carbon. Biomolecules, the complex organic molecules of life. Proteins, carbohydrates, lipids, nucleic acids. Carbon cycle, the movement of carbon between the atmosphere, oceans, land, and living things. Fossil fuels, coal, oil, natural gas formed from ancient organic matter. Hydrocarbons, compounds containing only carbon and hydrogen. Polymers, large molecules made of repeating smaller units. These terms really capture the essence of what we've been discussing.
Okay, let's try to synthesize all of this. Carbon, this seemingly simple element, element number 6, it's just absolutely fundamental, isn't it? And possesses this incredible versatility.
It really does. From the graphite in your pencil to the diamond on a ring, from the very building blocks of life proteins, DNA, to the fuels that have powered our civilization.
And even to the air we breathe, affecting our climate, carbon is truly at the very heart of it all.
It is. This deep dive, pulling from all these sources, has really illuminated just how interconnected everything is. From the smallest atoms bonding in specific ways to the vast planetary cycles operating over millennia.
It's mind-boggling, really.
And this leads us, I think, to a crucial question for you, the listener, to consider. Given carbon's indispensable role, its centrality to life and energy, and our undeniable dependence on it, what are the most promising pathways toward a sustainable future?
Yeah, how do we balance things?
How can we reconcile our energy demands, our material needs, all based heavily on carbon, with the long-term health of our planet? Keeping in mind all the complexities, the trade-offs, the scientific understanding, and the uncertainties we've explored in this deep dive.
It's a profound question, and definitely not one with easy answers. We really encourage you to continue your own exploration into these fascinating topics.
Absolutely.
Perhaps something we've discussed today has sparked your curiosity. Maybe it's the future of clean energy technologies, or the ongoing research into carbon capture and storage, or maybe the amazing science behind the new materials that shape our world.
There's so much more to learn.
There really is. This deep dive into carbon chemistry, as complex as it is really just scratching the surface.